So, good morning, everyone. I'm Alessio Carpegna, and today I will present the work I did during these years, during my PhD, which is about energy-efficient neuromorphic hardware, and in particular, the design and optimization of brain-inspired computing paradigms for spiking neural networks. So, let me give you a little bit of background and reasons for this work. Basically, artificial intelligence is revolutionizing a lot of fields thanks to its capability to process and analyze data, to recognize patterns, and to take intelligent decisions. And the fields in which it is applied are many, and they are growing. So some examples are healthcare with personalized medicine and smart diagnosis. Autonomous systems like autonomous cars, which are the current trend in car industry, drones and robots, and new frontiers like space, energy, and smart infrastructure. The main problem we face nowadays with AI is power consumption, because the approach is based on a cloud computing. So generally data are collected by the systems, are sent to very powerful mainframes. The artificial intelligence model is executed there, and then the results are sent back. This requires a large bandwidth to send data back and forth. It has an unpredictable latency because it depends from the availability of the internet. And it has also security issue because I need to share data from the system where I'm collecting them to the cloud. A possible solution is to execute the AI model at the edge locally. And when I talk about the edge, I mean the opposite of the cloud. So the cloud is this centralized approach in which the mainframe computes everything. The edge is everything that stays at the boundary of the system. And the main problem with edge is that we have limited resources because the area is limited. And so we have limited availability of power, memory, and processing, limited cooling. And we need generally to balance many tasks. So we are not only executing the AI model, we do it in parallel to other things. One possible solution, at least the one that we decided to explore, is neuromorphic computing. So we know that the brain consumes around 20 watts of power, which is orders of magnitude below the power consumed by these powerful mainframes. And this efficiency was reached over millions of years of evolution. So why don't we take some inspiration from this efficiency, from this evolution? In my thesis, I explored the field of neuromorphic computing from different perspectives. The main core of my work was the development of the design of specialized FPGA neuromorphic accelerators. Then I tried some techniques to automatically configure this network, to find the optimal configuration of this neuromorphic system through automatic design space exploration. And then I also explored something more algorithmic, trying to apply some techniques of continual learning to spiking neural networks. And finally, during my abroad period, I also approached the field of analog neuromorphic computing, and I applied to earth rate monitoring. So let me first start by briefly explain what neuromorphic computing is and what are spiking neural networks in particular. Spikes can be considered the biological information units. So they are all or nothing pulses. And this is the way in which nature, this is the way that nature found to make the communication robust to noise and reliable over long distances. Since they are all or nothing pulses, they bring basically a binary information. So either they are present or they are not. So to encode more complex information, we can use groups of spikes using their firing rate, their timing, the patterns of the spikes that are received from multiple inputs, and these sort of techniques. And the good point of spikes is that they are efficient. They represent a good balance between computational power and low energy use. And this is true in biological systems, in analog neuromorphic, and also in the digital domain. I will show the results in a while. So we have neurons that talk with these spikes. The point is how the neurons react to the spike, how they integrate and process them. The first model for spiking neuron models were started from biological observations. The most famous one is the Hodgkin-Huxley, which was obtained by the observations on the current propagation over a squid giant axon. And then different degrees of simplification were applied to this model. In particular, one of the most common families of spiking neurons are the leaf-based neurons, so leaky integrate and fire neurons. These balance quite well the biological plausibility with computational efficiency. And basically, these models, the neurons as RC circuits with an exponential decay and with a threshold plus reset mechanism for the generation of the spike. Here on the top, you see some examples on temporal evolution of a neuron membrane over time. So from the bottom to the top, you see the input spikes that stimulate a quantity. For example, if you look at the central model, they are simply weighted by the synapse, the input synapses, and then they are integrated by the neuron, and in particular by the membrane of the neuron, which accumulate charges. And if this membrane exceeds a threshold, the neuron generates a spike. There are different models in this family with different degrees of complexity that are the ones that I represented here. When working with spiking neural network, there are two additional topics which must take in consideration and which were not the core of my project, so I only briefly present them to explain the next step that I implemented. The first one is how to encode the information into spikes, because information in nature and the information that is collected by sensor is not natively in form of spikes. So the first point is how can we encode this information into spikes? And how can we decode the output of the spiking neural network to understand what the network is classifying or is doing in general? The other aspect is training. And since, again, this was not the core of my thesis, I prefer to use the more robust methodologies, which are supervised methods adapted by artificial neural networks, and in particular, backpropagation through time with surrogate gradients. Now, as I said, the main core of my PhD was the development of these hardware accelerators for spiking neural networks dedicated to FPGA. And the final outcome of this work was Spiker. The first point is, why do we need to accelerate spiking neural network? What does we mean with accelerating spiking neural networks? If we look at the approach that is used in classical computing, like general purpose computers or embedded platforms, generally the computation is based on a single powerful computational unit, a CPU, and a large memory or a single memory from which the CPU is fetching instructions and data. But if we look at the way in which a biological brain computes, this is completely different from this approach. We do not have this strict separation between a central computation and the central memory. Memory and computing are co-located within the brain, and the computation is based on small and simple computational units, which are interconnected through synapses, which can be modified and store the memory around the brain. So the point is to try to reach, try to find a computation which is nearer to this approach, which is more similar to this approach, to make the execution of spiking neural networks more efficient. We have different techniques to do this, and in particular, the development of specialized hardware circuits. And we can do this mainly in two ways. So creating dedicated ASICs, so circuits that I design once and they are fixed. I cannot modify the hardware after that. I can in some way reprogram them, change some parameters, but the hardware is fixed. And in this case, I separated them into two families. So large-scale ASICs, which are generally dedicated to modeling large-scale spiking neural models. Here I represented them in the green bullet. My definition is sort of large because I also included Spinnaker, which is not namely an ASIC. It is more an ensemble of devices, but this is the grouping that I did. Then there are small ASICs, which are more smaller circuits, which are dedicated to a specific application. These are even less configurable because, okay, I can change some parameters, but the hardware is really fixed. And then the second approach is to target reconfigurable hardware, so to develop reconfigurable circuits for reconfigurable platforms, in particular FPGA. And you see in this cost configurability chart that they are the most configurable because I can reconfigure the hardware itself, and they are the cheapest because I do not need to recreate the hardware if I change the circuits. I can reprogram it. And additionally, many embedded platforms already include FPGA, so I do not need to add anything to the system. I can simply put my accelerator on top of the FPGA that is already present. So if we look at how Spiker is organized, what I tried to do was to exploit this reconfigurability at most. So to have a model that is modular, so I can reconfigure it, and I can tune it for the specific target application. I targeted clock-driven architectures with some interesting findings that I will show in a while. And if we look at how the computation is organized, you can see that we have a central control unit, which is the network control unit, which manages the flow of spikes from the input to the output. And basically layers are updated in a sort of pipeline way. So they are updated in parallel and they process this information that flows. The second step is a layer control unit, which controls the parallel execution of neurons within a layer. So we have 2 degrees of parallelism, the layers and the neurons. And finally, the neuron control unit, which processes spikes sequentially. So in this case, the parallelization is limited to the parallel execution of neurons and not to the parallel processing of spikes. Since we had access to reconfigurable hardware, I also tried to give the possibility to reconfigure the neuron model itself. So one can decide to reconfigure the network, but also to change the model of the neuron. And the most complete model that I created is includes a leaky synaptic integration plus a leaky integrate and fire model. So there is a first step in which the synaptic currents integrate the spikes, and it also has this exponential leakage. And then this current is integrated by the membrane potential into a second step. So we have a 2 steps integration. If we remove the first step, the first leaky step, we obtain a simple leaky integrate and fire model, which is the one that I described before. In this case, the spikes are simply weighted without any decay, and then they are integrated in a single step by the membrane potential. And finally, if I remove also the exponential decay, in this case, I obtain a simple integrate and fire model. There is no leakage. You see that the membrane is stimulated, and in absence of stimuli, it keeps a constant value. One of the contributions in this work is that I completely avoided the use of multipliers, which are kind of an expensive hardware block in FPGA. So you see that the good point of spikes, as I was mentioning, is that they are binary, so zeros or ones, so the multiplication becomes a simple selection. And you see highlighted with the symbol of the major, I replaced the multiplication required for the exponential decay with a simple shift, bit shift. Finally, the degrees of complexity in configure this hardware are many. So there is the need for advanced hardware design skills to put these blocks together. And there are many steps involved. I need to train my network to optimize it, to quantize its parameters, and then to translate it into an hardware description of the network. To simplify this process, I developed, first of all, an automatic VHDL generation tool, which is able to start from a high-level description of the network, and it automatically generates the VHDL code, which describes the hardware architecture. And then I embedded this into a Python framework, which automatized all the steps. So it takes a high-level description of the network, it trains it on a dataset that I provide in input, and then it automatizes also the optimization part in which it performs a grid search between many quantization parameters, and then the results is passed to the VHDL generation for the translation into an hardware accelerator. To test the accelerator that I obtained, I targeted 3 applications. The first one is the MNIST, which is not really a task which is suitable for spiking neural network, but still it is a common benchmark in the machine learning domain. And so I used it to compare my architecture to others. And then I targeted 2 more spiking-friendly datasets, we can say, which contain temporal data, so something for which spiking are more suitable, which are audio datasets. In particular, the spiking Heidelberg digits, which is a set of already encoded data, so they already come in form of spikes, and a second dataset in which I applied a custom encoding, which is the audio MNIST. Now, if we look at the absolute rankings of my accelerator, on the top you see the numerical results, the metrics that I measured in the accelerator. And you see that I highlighted two of them in green, in particular the power consumption, which is 180 milliwatts, and the area with 7,612 lookup tables. The first interesting point is that if compared to other FPGA accelerators for spiking neural network, Spike resulted the best in terms of power consumption and area. And here we have the first strange thing, because it's a clock-driven architecture. So I wasn't expecting it to be the best in terms of power consumption, even when compared with event-driven architectures. But the point is that we are targeting small accelerators, so small applications, with digital accelerators, and we are targeting a platform which is FPGA, which is intrinsically clock-based, so we are kind of matching the computation approach with the platform, and densely connected solution. So in this context, it seems that the tuning of the hardware that we applied is effective. So instead of searching for a more complex algorithm, simplify the architecture and really tuning the hardware towards the application seems to be a good approach. Then if we look at the relative rankings, so how Spiker places with respect to other accelerators with other metrics, we see that it is Pareto optimal for power accuracy trade-off. So it's not the absolute best, but it is on the frontiers of the best accelerators. It is Pareto optimal for area and accuracy trade-off. And it is the joint best, so together with another accelerator, it is in that sweet spot in which both the latency and the power are minimized. So we are really optimizing the architecture towards this application. It is the best for area and power and the best for area and latency trade-offs. It still lags a little bit for the accuracy part because we focus more on the hardware optimization part. So there were other accelerators that pushed more towards accuracy. So in this case, we are a little bit behind. Then I performed an analysis of the performances of the accelerator with respect to the input activity, so to the density of the spikes that I provided input. And here I found my second interesting result, which is that the power for simple leaky integrated amplifier model, so without the leaky integration in the synaptic part, for them, the power is constant or even decreasing with the input activity. And this is the second strange thing, because I'm increasing the density of the spikes, so the amount of spikes that I provide in input, and the power is, even if slightly, but it is decreasing. So I worked a bit on the thing. I needed to think a bit on the thing. And again, let's think about the fact that the architecture is clock driven. So it is computing even if there are no spikes. At every clock cycle, it is computing. And this is the first point. And then if we look a little bit closer to the control unit which governs the architecture, we see that if we receive spikes continuously, the network is kept into the integrate state, and it continues integrating spike. If we have a situation in which there is a spike, then there is nothing, then there is a spike, then nothing, and similar, the network continuously switches between states, in particular between the integrate and leak, if there is no threshold exceeding, or between the integrate and fire. So we have this sort of ping pong between states, and this becomes the dominating part of the power consumption. So the arithmetic part is very simple. The control part becomes the dominating part. This is not true for more complex architectures, so like the one that I showed before with synaptic leakage in input. In this case, you see in the red curve above that the power is increasing with the input activity, so more intuitive behavior. If you look at the latency, it is increasing almost linearly with the input activity, and overall, the energy consumed by the accelerator to process all the input spikes is, as a consequence, increasing also with the input activity. Now, we have a tool that allows to automatically configure the network and generate the hardware accelerator. The point is, I need to start from a high-level description of the network. How can I optimize that description of the network? Can I find the optimal configuration of that network? We tried to answer this question together with Dario Padovano, which was a master thesis student, with SpikeExplorer, which is an automatic design space exploration tool for spiking neural networks on FPGA again. The point is that if I want to configure the network, there are many degrees of freedom in the configuration. So I can choose the number of layers, the number of neurons, the model of the neurons, the internal parameters, the parameters that are used to train the network. So there are really many parameters involved. So the choice of this optimal architecture is not trivial. And additionally, I have multiple objectives because I'm targeting an hardware implementation of the network. So together with optimizing the accuracy of the model, I also want to optimize power, latency, and area, for example. So a manual configuration can be hard, and we explored some automatic techniques, and in particular, automatic design space exploration. We used Bayesian optimization for this purpose, which is an iterative process in which a surrogate model guides the optimization, and in particular tries to find between all the configuration, which is the optimal one, which will reduce a specific target quantity or maximize it. It is fast to converge, and it is good for larger search spaces and complex functions like spiking neural networks are. And additionally, it is parallelizable. So executing it on a computer which gives accessibility to parallelization, it is also faster to execute. So we developed this framework as a modular Python tool with a closed loop architecture. The core of this framework is a multi-objective Bayesian optimizator, which is based on the AX tool developed by Meta. And as optimization metrics, we targeted accuracy, area, latency, and power. So we gave the possibility to the user to select which is the metrics to which he wants to give more priority in the optimization. The tool is compatible with any user-defined neuron characterization. So I expect to receive a characterization of the neurons that I need to instantiate in terms of power, latency, and area. But since we had access to Spiker, we applied a library of neurons which was characterized with Spiker. We explored 4 different neuron models. In particular, 2 of them, all of them are leaf-based, so again, leaky, integrated, and fire. 2 of them are simple model without any explicit recurrence between the neurons, so they compose feed-forward networks. And we explored solution in which we also included recurrent connection within the layers. We applied this again on the MNIST, and what we found out with the tool was that simpler architecture, we can say without any recurrence within the layer, and smaller network architecture were the best fit for this kind of application. Then we applied the tool again on spiking Heidelberg digits. And in this case, we found that a recurrence between the neurons of the same layer can be beneficial for the performances of the network. Still, the smaller networks, so less than 250 neurons, were okay to classify this model. So overcomplicating the network doesn't add any performance. And finally, we tested it on the DBS gesture, which is a data set of gestures recorded with an event camera. So they come in form of spikes. In this case, a recurrent model, so with internal recurrences, and larger neuron network models with more than 250 neurons also were the best fit. So the data set seems to be a little bit more complex, and the network needs more complexity. So what this tool already enables us to do is to identify which is the best, to give an idea of which is the best architecture if I'm targeting a specific task. So if the task is simpler, the network, the resulting network will be simpler. So it already gives an idea of the direction to follow in configuring the network. And then we applied this tool to try to further optimize the architecture that we obtained with Spiker. And in particular, we started with the same architecture as before. So looking at trying to optimize the internal parameter, the training process, and so on. And since the architecture was the same, basically the area and power consumption were the same as before, but the tool was able to optimize the latency, bringing it from 780 microseconds to 120 microseconds, with a 2% improve in the accuracy. So we have a tool that identifies the best model for a task and allows to optimize already configured architecture. So this was sort of what we were searching for. Currently, I need to say these results were even made better because I have two Padovans. Then this slide is not really correct because I'm a Sith, but this was the only picture that I had as in form of a Jedi warrior. But they presented a modified version of Spiker to ICEEP 2025, which is a challenge. They modified the architecture, they further optimized it, and they obtained an accuracy of 97.5% with a latency of 53 microseconds. So we are really minimizing it. The power consumption was slightly increased, but this was the price to pay to try to optimize the latency. The main goal of the challenge was to optimize latency and accuracy. Then, as part of the PhD, I collaborated with a group from Bologna, and in particular from the Pulp group. And I worked with Alberto De Quino and Davide Nadalini, which are two PhD students under the supervision of Francesco Conti and Luca Benini. And we worked together to try to apply continual learning techniques to spiking neural network. In particular, we tried to apply compressed latent replays to spiking neural networks. So what is the field of continual learning? In the applications that I just presented you, the network was trained once, and then once that I tuned it on a specific task, I didn't modify it anymore. So it was applied on the task for which it was trained, and that was it. In continual learning, I have a continual adaptation of to an evolving environment. So the network continues to learn even when it is deployed in the real world, we can say, but without forgetting previous knowledge. This is an important point. So I want to learn new information without forgetting what I learned before. And typical applications for this are to compensate data distribution shifts, because, for example, I pre-train my network on a set of data, but then when I really use the network, the set of data that it sees can be different because I have different conditions in the environment. So I want to continuously adapt my network to the evolving data. User adaptation. So, for example, I train my network on a generic data set, and then I want to specialize it on a specific user to improve the experience of that user, or to learn new tasks on the fly. So it learns some classes, and I want the network to learn something new on the field. There are different techniques to do this, so to learn new information without forgetting the previous one. The first family of methods are rehearsal-free methods, which rely on architectural changes, so regularization or similar. The good point is that these methods are lightweight, but in general, they show lower accuracy and robustness. And there is a second family of methods, which is rehearsal-based. In this case, when I teach the network something new, I also replay some of the previous data in order not to forget what I learned. The main drawback of these techniques is that it is memory intense, but it is more mature. So it shows higher accuracy and robustness, and in general, the methods are simpler. For these reasons, we decided to explore this family of methods, also because it is a field that is poorly explored for spiking neural networks. What we try to apply in particular is the concept of latent replay. This is an algorithm that was developed for convolutional neural networks. We tried to move to the spiking domain. And the idea behind this method is to pre-train the network on a set of data, and then to freeze the first n layers of the network, which will behave as feature extractors only. I will not train them anymore. And then when I want to add new data to the network, to teach new data to the network, I only train the last part, the last layers of the network. So I simply fine-tune my network on the new task. And instead of replaying the full input of the network, I replay only the latent activation from the layer that I want to train on. This already has two advantages. Okay, my slides canceled. I had an advantage symbol, but the retraining is made simpler because I simply need to retrain the last part of the network. I do not need to retrain everything. And if I have an architecture in which layers are narrowing towards the output, that is the typical application for the typical architectures for classifiers or feature extractor, I already have a spatial compression. So instead of replaying, and so instead of keeping in memory all the input data, I keep in memory also only the activation from a layer on, and if the layer is smaller, I already gain some space. The drawback is that I still need to store the full spike sequences. So the question that we posed ourselves was, does the network really need the full sequences of spikes, or can I provide an approximated version of one? It is similar, I think it's similar to what happens in a biological brain. So when I need to remember something, do I need the specific sequence of exact spikes that I received when I saw that thing, or can I have an approximated version of it? So we try to apply a lossy compression when storing this activation, trying to compress the sequence. And in the example image, you see that we started from a sequence of 3 spikes, for example, and compressing them, we lose 1 spike. So we approximate it to 2. And then at runtime, we decompressed the sequence in order to correctly replay it and make the network remember previous information. We tested this again on the spiking algebraic digits, which unfortunately is one of the few purely spiking benchmark datasets for spiking neural networks. So I used it along many of the works. And this is a dataset made of 12 speakers pronouncing numbers, and in particular numbers divided into 20 classes, 10 English numbers and 10 German numbers. We used a fully connected network with interlayer recurrence, similarly to what I showed before, with 5 narrowing layers, 700 inputs, and then 200, 150, and 20 neurons. So we have this narrowing architecture. We targeted, again, leaf neurons. We applied, first of all, the technique to a sample incremental scenario in which we pre-trained the network on 11 speakers, and then we tried to add the 12th speaker afterwards. In this scenario, what we observed is that the technique of latent replays behaves better with respect to the classical rehearsal method in which I replay the full input data, which I called here naive rehearsal. We have a 2% accuracy improvement. And additionally, since we are replaying the activations on the first layer and not the full input, we already saved 3.5 times the memory. Then, if we look at how the compression behaves, we observe that it is better if applied to deeper layers. And this is reasonable because if I compress the input, I lose too much information probably. And looking at the results, we obtained, applying latent replays on the 3rd layer, we obtain the same accuracy, basically, that we had with a classical rehearsal approach, but with a memory saving of 70 times. So quite good. And if we accept to lose a 2% of accuracy, we pushed the memory saving to 140 times. We then applied the same method to a class incremental scenario in which we pre-trained the network on 19 classes, and we tried to teach the 20th class afterwards. And the observations were very similar. So better accuracy, in this case with 7 times memory saving. And again, if we apply compression, if we accept to lose 3% accuracy, we saved 70 times the memory, again, and with a 4% accuracy loss, we saved 140 times the memory. In this case, you see that the performances are slightly lower, but because the class incremental scenario is a little bit more complex. The final task on which we tested our method was a multi-class scenario. So we pre-trained our network on 10 English classes, and then we progressively added the German ones. So what we tried to do is, we can say, to teach German to the network. The network already knew English, we tried to teach German to the network. And what we observed is a 2% accuracy loss on all the classes. So while the network is learning German classes, it forgets something on the English ones. But the German classes are learned quite well, with an 88% accuracy. We applied a compression ratio of 1 to 2. So instead of storing the full sequence, we compressed it to a sequence which is half of that. So we already saved 50% of the memory in time. And we applied replays on the 2nd layer of the network, saving an additional 14 times memory. What we observed is that the network generalizes quite well to the new language. So you see that the accuracy overall increases up to almost the 80%. So in the beginning, it only knows English. At the end, it also understands German. Finally, as part of my PhD project, I also did some months abroad in the Institute of Neuroinformatics, and I worked under the supervision of Giacomo Indiveri, and I worked together with Chiara De Luca, Elisa Donati, and Federico Emanuele Pozzi. And I worked on developing solutions for analog neuromorphic computing in this case. And in particular, I developed neuromorphic heart rate monitors with neural state machines for monotonic change detection. Which is the idea? The goal of the work was to detect the agitation into patients affected by dementia. And this agitation has many symptoms. The main one is the heart increase, a slow heart increase. And then I have other symptoms like an increased sweating, decrease in body temperature, screams, curses, and similar. The current approach involves a caregiver which continuously monitors the patient and, if necessary, he intervenes. The alternative would have to have a real-time, always-on monitoring system which monitors the patient and alerts the caregiver only if needed. The problem is that if I use a battery-powered monitoring system, the patient forgets to recharge it. He forgets to put it on. So we need a system that stays on for days, if not weeks, so we can put it on and forget about it. And neuromorphic solutions, in particular analog neuromorphic, can be really the solution in this case because they have a power consumption which is ultra low. So the kind of application that we want to target is this. We have an increase in this agitation state, in particular in the heart rate, and we want to detect it. We have a first problem, which is the agitation takes minutes, if not hours. So it's a slow agitation over time. But the problem is that analog neuromorphic systems try to emulate the biological time constants, and so have time constants of milliseconds. So the first question is, how can we match these two time scales, minutes, hours with milliseconds? And the second question is, how can we follow only the monotonic increase, ignoring these local peaks, so this local relaxation, or this peak into the heart rate, for example, if the patient is scared or if he's doing activities of some kind. To answer the first question, I explored the field of excitatory-inhibitory balanced networks. The first point to notice is that when we work with analog neuromorphic chips, we generally work with populations of neurons, not with single neurons. And this is because the noise within the system and the mismatch in the technology makes the behavior of a single neuron very different from the behavior of another. So generally, we work with populations to average the activity of the neurons. And these excitatory-inhibitory balanced are groups of neurons which include a self-excitation and a self-inhibition, which, if it is well tuned, allows the network to keep an activity also if I remove the input. So you see an example on the left in which an input starts the population. So I provide input spikes to the network, and the network starts to generate spikes in turn. When I remove the input, if the network is well tuned, it will continue to fire with a lower rate, but it will stay active. And this can already solve the point of make the time constant longer. We can organize this excitatory-inhibitory balance network into more complex networks like winner-take-all network, which are networks in which there is a common inhibition and multiple excitatory populations connected to these inhibitory populations. If you look at the left, I reported an example of behavior of this network. And so if I start stimulating a state, for example, state 0, you see that when I provide input 0, both state 0 and the inhibitory populations are activated and are balanced. Then, as I said, if I remove the input, the population continue to fire with a lower rate. But then at a certain point, if I stimulate another state, for example, state 1, I activate state 1 plus the inhibition. I have state 1 and the inhibitory population, which are balanced, but the inhibitory population is no more balanced with the state 0. So the inhibition in this case becomes stronger than the excitation. And so state 0 is turned off, and the network switches to state 1. So this is the way in which I can implement simple state machines with analog neuromorphic chips. The problem is that we said that we want to follow only the monotonic increase of the agitation. With such kind of networks, all the possible transitions between states are allowed. So my contribution was to modify the network, to add a part to enable only the monotonic, to follow only the monotonic increase. And in particular, I added a set of gating populations, again, excitatory inhibitory population, which continuously inhibit the states. And I use the concept of disinhibition, which is I stop the inhibition of the states in which I can go, in which the transition is allowed. So I disinhibit only the states towards I can move. In this case, you see that if I progressively stimulate the states, I progressively stop the inhibition of the next state, and I can transition to that. And then I re-inhibit the other states, all the other states in which I cannot go. So this intrinsically guarantees that the network only follows the excitation. The only case in which I can go back towards the lower state is if I have a complete relaxation, so I can follow back into state 0. I tested the method on a dataset of heart monitoring during exercise, which quite well represents the kind of application that we are targeting. There were recording measuring the ECG of the patients plus other metrics during walking, running, easy cycling, and hard cycling. There were 9 subjects, and the recording lasted for 6 to 10 minutes. So already the time constant that we are looking for, the time duration that we are looking for. And here I reported the results. So you see on the top the evolution of the heart rate, which is increasing, and there are some slight relaxation portions during the activity. You see in the direct translation of the signal into spikes that there are portions of the spikes which are overlapped. We have these, we are following this partial relaxation, for example, between the green and orange, we have this partial relaxation. If we then stimulate our network, here there is the input of the network, you can see that instead the network follows exactly the monotonic increase. So what I reported there is the activity of the populations of neurons, and in this case, only the monotonic increase of the heart rate is followed. The very impressioning thing is that all of this is done with a power consumption of 90 microwatts. So really nothing. So this confirmed the fact that this analog neuromorphic approach can really solve the problem that I want to target. So what I have to say is that I really enjoyed this PhD path. It all started with a master thesis together with Stefano and Alessandro. And if I look at where we are now, we have students which are competing in a challenge, and we know that they are in the first 3 places, and we will discover which of them. We have another student which is working on energy efficient accelerator, so he's continuing my work. In particular, is comparing event-driven architecture and clock-driven architectures due to this interesting finding that we had on clock-driven architectures. We are working as a group to hardware interfaces for spiking neural networks, and we are doing this in collaboration with Zurich. And we are also trying to approach the field of on-device learning and more bio-inspired training algorithm with respect to the ones that I used, which are supervised. But most than everything, I need to thank the group in which I was, because these were 3 of the best years of my life, and this was mainly thanks to the group in which I was. So thank you guys, thank you Stefano and Alessandro for everything. I learned really a lot, and I enjoyed every moment of this path. Thank you.